samples for two separate samples, okay? And so we're going to look at different varieties of things. And so you kind of got to be able to see what you're working with first before you know how to proceed. So the first one we're going to talk about is how to find the confidence intervals for the difference of means whenever both the population standard deviations are known, okay? And so basically, you're going to have some sample means from two different samples, two independent samples, and then you're going to have two sample sizes there. And you can use the formula. I'm going to do it backwards today. I'm going to do calculator first and then formula second, so you can kind of decide which way you want to do it. In the summer of 1988, Yellowstone National Park had some major fires that destroyed large tracts of old timber near many famous trout streams. Fishermen were concerned about the long-term effects of the fires on these streams. However, biologists claimed the new meadows would spring up under dead trees that would produce a lot more insects, which would in turn be better fishing ahead. Guide services registered the park by the daily catch for fishermen over the years. So basically, we have a number of day. They kept track of the number of days. Suppose you're a biologist studying fishing data from Yellowstone streams before and after the fire. Fishing reports include the number of trout caught by day by fishermen. So there's a random sample of 167 reports for a period before the fire that showed the average was 5.2 trout per day, and the standard deviation for this period is 1.9. So we know the population standard deviation. We know sigma. Another random sample of 125 5 years after the fire. 5 years after the fire showed the random sample that was the sample mean was 6.8 trout. Soon the standard deviation was 2.3, the population standard deviation. So here's the thing. We have two separate samples before the fire, after the fire. It's means, so two sample means, and the population standard deviations are known. So for each sample, what is the population? So the population is I guess you could say the number of trout caught per day for at Yellowstone or wherever you would say, or is this at Yellowstone? Yes, at Yellowstone. Uh, so the population, so the first sample is the number of trout caught per day before the fire. Okay, and then the second sample is the number of trout caught per day after the fire. And so we're trying to see, is there a difference in the amount of trout caught before and after the fire? Day after the fire. Whoops. Okay. Are they samples dependent or independent? So when you have dependent samples, there's pairing involved. Like you're pairing like one, like it'd be like pairing one fisherman with another fisherman, another. So you'd be pairing them like by either by fishermen or by some other way. Here, what we did is we did a sample before and a sample after. So these are called two independent samples because there's no pairing involved. So this would be independent because there's no pairing involved. We didn't pair up observations. Okay, so there are procedures whenever there's pairing involved. Okay. So now we're going to compute a 95% confidence interval for the difference in means. Now, here's the thing. First off, we have to establish it's means and the population standard deviation is known. If this is known, I'll make a note. If sigma is known, we do a z, or we do z. If it's unknown, we do a t. Okay? So now it's for difference of means. I'm going to show you how to calculator first, and I'll show you by hand. So how do you do this in the calculator? You go to stat, test, and it's a two-sampled z interval. So stat, test, and we use z whenever the population standard deviation is known. Two-stamp z int. Okay? So stat test. You also could do, wait, actually, you cannot do this one in salt. This one's the one you can't do in salt. You'll do stats here, okay? And all you have to do is fill in the information. So you just have to fill in the information. Sigma 1 is right there, is 1.9. One's 1.9. Sigma 2, I'm just copying this from here, is 2.3. X bar 1 is 5.2. N1 is the first sample size. N1's 167. X bar 2 is 6.8. And N2 is 125. All right, I'm not that smart. All I did was I just copied that from the 5.2, 167, 6.8, 125. So all I did was copy that from the problem. 1.9, 2.3, 5.2 is X bar 1. The first sample size was 167. 6.8 was the second one. And the confidence level is 95%, so 0.95. Sea level, 0.95. Okay, calculate. So there's my confidence interval. It's negative 2.096, negative 1.104. That's my lower bound. It's my upper bound. Okay, so lower bound, upper bound. There's your. Okay. All right, now we're going to interpret the interval, and I was going to try to kind of customize this based on your homework a little bit. So, how do we interpret this? We could say, which actually they do a little different. So let's go back to. I'm going to say we are 95% confident that the interval negative 2.096 and negative 1.104 um, fish per day uh, contains the population difference in average fish caught per day before and after the fire. Okay. Uh, that's a lot of writing, I know. So it's a lot of writing. We're 95% confident the interval negative 2.096, negative 1.04 fish per day contains a population difference in average fish caught before and after. So basically, what this means is it's all negative. And so what that means is the difference is negative. It was before minus after. So it looks like there was significantly more fish caught after the fire than before the fire, because before, if you do before minus after, for this to be negative, the after has to be bigger. That means there is more caught after the fire than before the fire on average. So that means the number of fish, the average number of fish caught increased after the fire. But all right, now this is optional. If you want to know how to do this by hand, I'll show you. So how you do this by hand, first thing we need to do is calculate the error. So completely optional. So error is Z of C times sigma 1 squared divided by N1 plus sigma 2 squared divided by N2. Z of C is the critical value, and so we know it's a 95%. So if I go to the front, I get 1.96. It's up front here. Since it's a Z procedure, I use these. 1.96. So 1.96 times the square root of 1.9 squared divided by 167. I don't like doing all this because I'm afraid I'm going to mess up somewhere. 2.3 squared divided by 125. And so all I did was plug in sigma 1. I'm just plugging in these values. Sigma 1, N1, sigma 2, N2. Now I'll calculate this. I can do all this at once. 1.96 times the square root of 1.9 squared divided by 167 plus 2.3 squared divided by 125, 0.04956, so 0.0, I'll go 3 spots. Or, I'm sorry, 0.49, I didn't mean 0. 0.496. So then what you do is, you now, to find the interval now, you're going to do the differences in the means. So the difference in the means, let's find the difference in the means next. The difference in the means is x1 minus x1 minus x2, which is 5.2 minus 6.8, which is negative 1.6. So you find the differences in the means. And so what you'll do is, you're going to take the differences in the means plus or minus the margin of error. So the differences in the means, negative 1.6 plus or minus the margin of error. 496. So if you don't get this, just use your calculator. That's what I would be doing. So negative 1.6 minus 0.496, negative 1.6 plus 0.496. And so notice there, when you do that, you get the interval negative 2.096 is less than mu1 minus mu2, which is less than negative 1.104. So that's how you do it by hand.